Hello students, welcome back to my YouTube channel. In this video, I am going to discuss about uniform circular motion. If an object is moving in a circular path, we can say that that object is in circular motion. In uniform circular motion, object is moving in a circular path with constant speed, not constant velocity. Constant speed means the object covers equal distance along the circumference in equal interval of time. Circumference means over this, like this surface. Okay, that is about the uniform circular motion. The example of the uniform circular motion, we can take it as the motion of a second hand of a clock. If you watch carefully, you can see that the second hand will cover equal distance in each second. Okay, so now we are going to study detail about the uniform circular motion. Okay, so I consider a body is moving in a circular path like this way. Okay, the radius of the circular path is r. Okay, the object is moving constant speed. Initially, the object is at P point. After some time, the object reaches to the point Q in delta t. Okay, after delta t time, the object reaches to the point Q. So, here I can say that this radius vector seeks an angle in that particular delta t time. So, that angle we will call it as angular displacement. So, angular displacement is the angle seeked by the radius vector in a particular interval of time. Here, delta theta is the angular displacement. Okay, what is the radius vector? You look at this. The radius vector is a vector. It is originating from the center and point at a point on the circle like this. Okay, this radius vector seeks an angle. That angle we will call it as angular displacement. Okay, it is possible to measure it. Yes, we can measure this value. For that, we are using a concept. If this object complete a full circle, then how much angle this will seek? Total angle of the circle. The total angle of the circle is 360 degree. That is 2 pi radian. Okay. So that time, what about this circumference? If r is the radius, the circumference is 2 pi r. So now you see, the circumference is 2 pi r divided by the radius. What do you get? You will get 2 pi. So from this, we can say that the circumference divided by the radius is angle. So here this distance, okay, that is delta s, like that angle. So from this we can say that angular displacement delta theta is equal to arc length divided by the radius. Here, delta theta is the angular displacement, that is equal to the arc length. How much is the arc length? That is the PQ length, that we already taken as delta S. And the time taken to reach the object from P to Q is delta T. This is the angular displacement. Okay, then what about its unit? SI unit is radians. Okay, normally we are using degree for measuring the angle. So we will see the conversion. If a body complete a circular rotation, total angle is 360 degree. That is equal to 2 pi radian. Okay, this is a concept we can use. By using this, we can find out the conversion. If this 360 got there, 1 degree is equal to 2 pi divided by 360. That is equal to pi by 180. So 1 degree is equal to 5 by 180 radian. Okay, this is the method we can adapt for the conversion. Okay, then next, in the linear motion, the displacement of an object divided by time, we will say that velocity. The similar way, in the circular motion, the angular displacement divided by time is called as angular velocity. So, angular velocity is the rate of change of angular displacement per unit time. Okay? Angular velocity is represented by a letter omega. Here, delta theta is the angular displacement in delta t time. So, omega is equal to delta theta divided by delta t. So, from this, we can say that angular velocity is the amount of angular displacement in unit time. Okay, then its SI unit is radian per second. Okay, this is the average angular velocity because this velocity measured in a particular interval of time. If we will measure the angular velocity at a particular instant, we will consider the limiting case. So, instantaneous angular velocity. Velocity omega is equal to limit as delta t tends to 0, delta theta divided by delta t. Okay, that we can write it as omega is equal to d theta divided by dt. Okay, this is the instantaneous angular velocity. Okay, so if a body is moving in a circular path, it have angular velocity and it having linear velocity. What about the direction of linear velocity? Linear velocity at a particular point is tangent at this point. Okay, so this is the linear velocity here. Okay, so if we calculate the linear velocity and the angular velocity, there is a relation between them. That relation we'll discuss now. Okay, so here, what about the angle? That is angular displacement. Delta theta is equal to the arc length delta s divided by delta t. Okay, then I am going to divide two sides. This is delta s divided by r. Okay, now I am going to divide the two sides with the delta t. So, delta theta divided by delta t is equal to delta s divided by delta t into 1 by r. Okay, then I am going to apply the limiting case. So, limit as delta t tends to 0, delta theta divided by delta t is equal to 1 by r into limit as delta t tends to 0, delta s divided by delta t. What is this? This is the angular velocity omega divided by is equal to 1 by r into this is the linear velocity. Okay, then so from this we can write it as the linear velocity is equal to omega into r, where omega is the angular velocity and r is the radius. The linear velocity is a vector quantity and the radius is also a vector quantity. To satisfy the vector relation, we have considered the omega also a vector quantity. Okay, and the direction of omega is found out by using right-handed rule. Okay, I will explain now how we can find out the direction of omega. If a body is moving in a circular path like this, okay, this is the center. So, place your right hand over the circle like this way. Okay, the curled fingers in the direction of motion. Okay, thumb is like this. So, you can get the direction is coming out. So, the direction of the omega is here in this direction. The direction is perpendicularly coming out from the plane of the circle. Perpendicularly coming out from the plane of the circle. This is similar to a screw. If you rotate it like this way, if you rotate it, what will be happen? It will be come out from it. Okay, if the screw is rotated like this, it will be come out. Okay, this is the way we can find out the omega direction. Here the omega direction is like this. Okay, then another case. If the body is moving in a circular path this way, then you apply the right hand. By curl the right hand fingers like this way. Okay, then the thumb is going into the plane. So going into, we will represent like this. So here the angular velocity is a vector perpendicular to the plane. Perpendicular to the plane and into the plane. Okay, then it is from the center. Okay, and the omega direction is like this. That is similar to the rotation of a screw. If you rotate a screw, if the screw is like this, if it is rotated, it will go into it. Okay, this is the way we can find out the angular velocity direction. The angular velocity omega is equal to delta theta divided by delta t. Angular velocity is a vector quantity. So angular displacement also a vector quantity. So the angular displacement have the same direction of angular velocity. Okay, then next we will see the relation between angular velocity and frequency. Okay, then if t is the time period of the circular path, then we can say that time period is equal to 1 by frequency. Then omega is equal to delta theta divided by delta t. If delta t is equal to the time period, okay, that means this delta t is equal to the total time. Okay, then what about the delta theta? Delta theta become total angle of the circle, that is equal to 360 degree, and that is 2 pi radian. Okay, so here from this we can write it as 2 pi divided by t. This is omega. 1 by t is equal to mu, so omega is equal to 2 pi mu. Okay, this is another formula for angular velocity. Okay, then in the linear motion, the velocity divided by time is called as acceleration. The same way, in the circular motion, the angular velocity divided by time is called as angular acceleration. Okay. So, time rate of change of angular velocity is called as angular acceleration. Angular acceleration is represented by alpha. So, alpha is equal to change in angular velocity divided by time. Okay, so this is equal to omega 2 minus omega 1 divided by the change in time. Okay, so the angular velocity is a vector quantity, so the angular acceleration also a vector quantity. Okay, then what about the direction of angular acceleration? Angular acceleration direction is equal to the change in angular velocity direction. Okay, then what about the SI unit? SI unit is radian per second square. Okay, this is the angular acceleration in a particular interval. So this acceleration, we can say that average angular acceleration. If we calculate the acceleration, that is the angular acceleration in a particular instant, we will say that instantaneous acceleration. So the instantaneous angular acceleration is the limiting case of the average acceleration. So the limit as delta t tends to 0, delta omega divided by delta t, that is equal to d theta divided by dt. Okay, so this is about the angular acceleration. Now we will see the relation between angular acceleration and linear acceleration. Okay, we already know that the linear velocity is equal to omega into r. Okay, In this equation, I am going to take the derivative on the both sides. So dv divided by dt is equal to, r is not to be possible to change, so it is a constant, we can take it outside. So d omega divided by dt. What is dv divided by dt? That is linear velocity divided by time. That is equal to linear acceleration is equal to radius into, this is angular acceleration. Okay, this is about the relation between linear acceleration and angular